Well, the metal additive manufacturing. So first of all, we would like to study about the Vader system, which is based on the magneto hydrodynamics liquid metal jetting process. So actually, we have Vader system's first prototype located in the Brinkmann lab, and our faculty member Denis Cormier has been highly involved in the research and development for the Vader machines. So as you can see in this illustration figure, um, the Vader machine consists of few parts. First of all, the biggest advantage for this manufacturing system is uh, it utilizes the coil as the building material instead of the metal powder, which is much inexpensive, much cheaper than the powder bed based metal additive. Also, as you can see here, the metal coil goes into here and it's melt, and the droplet will be uh, jet onto this platform. As you can see here, there's a coil. Basically, this coil runs this um, square waveform, or the pulse waveform, controls the speed and frequency of this droplet, such that each of the layer will be formed through this jetting process, and so on and so forth. As I mentioned, the cost is the biggest benefit for this process. For other metal additive manufacturing, they utilize the metal powder. So the metal powder is much more expensive than um, than the metal with the same amount of weight, but in different form, like in the bulk form. It's much more expensive. It's like 5 to 10 times more expensive, right? So it, to make the metal additive more popular, it is essential to reduce the cost, right? Another advantage is there's no need to recycle the metal powder for the Vader system machines, right? Because in the uh, process using metal powder, you have to always recycle. Basically, you need to fill the whole um, the whole vat, whole box full with metal powder. And each of the time, even you do not need that much. You still need to fill the whole space. Then for the one in sorry, for the metal powder have not been used in the building, you have to recycle them. Then it brings another problem. For many applications like those aerospace or biomedical applications, uh, they require to trace the material. That means if you mix different powder together, you have to trace which powder you used and which powder used for what portion of the part, and that will bring a lot of trouble to the manufacturing process. Also, the powder is not that safe to handle. Especially some of the aluminum powder, right? It's very easy to get on fire or even explosion. So it requires extra handling and also permission to process with such powder. All these will not be a problem for the Vader system machines. Also, the printing speed um, for this process, it could be also another potential benefit because we could integrate multiple nozzles to the machine, and in the future it could be further sped up. Again, without powder, you have a lot of benefit without the loading, cooling, or uploading times. So I will let you see this video and see how it works. And as you can see, it shows the working process of the Veda. Here is similar to the fuse deposition modeling, and the wire is fed to the heating mechanism and jet onto the platform. So there are a few parameters for this process, for this machine. First of all, the nozzle temperature, if we use the aluminum material, it used to be the 850 to 900 Celsius. Also, the platform is heat up to certain temperature to speed up the printing process, which is 400 Celsius usually. Also, the nozzle has 500 micron diameters. The droplet firing frequency is in the unit hertz, and usually it measures the drops per second. Here shows you some process simulation. As you can see here, the magnetic field is generated to control the droplet. And in the right-hand side figure, as you can see, there are two droplets. Let me see if I can make it play. Yeah. Okay. So as you can see on the right-hand side, there are a big and a much smaller droplet formed during the jetting, in which the smaller drop is usually called the satellite drop. It is undesired, as I mentioned, in the material jetting process. This kind of satellite drop will cause accuracy problems, because you just imagine the platform is moving, and if there's some satellite drop, it will create the excess trace on the platform, such that it will make the printing inaccurate. So let's look at a slow motion of the jetting. As you can see here, it's just like a continuous stream, but in fact, it's the droplet jets in a high frequency. So you can see this here shows the slow motion of the jetting, right? Okay. Also, if the droplet is jet in a high frequency, or the overlap of the droplet the portion of the overlap is higher, you could see from the thermal temperature point of view, if how the difference. You can see if the droplet is jetted in high frequency, this is low, this side is low, and this side is high. For the temperature, you could see for the one jetted in high frequency, basically you have more energy per unit time, and such that the temperature is much higher. Similar case happens if you have high overlap versus the one with low overlap. So for the high overlap, you again have more thermal energy observed during the process. And that will affect the density and the microstructure of the printed part, as we will discuss in the future slides. So also in this figure, it shows for the left corner and right corner, it shows two extremes. So for the left corner, it shows the minima drop spacing, and for the right corner, it shows the minima jetting frequency. As you can see, obviously with these two extreme, they are not in good quality, printing quality. What we actually looking for is something like this. So the trace will more like a straight line. It's not too much. There are not too much material or too less. Too little. Basically, that's the desired trace we would like to produce using the printing process. Also, we can find some idea about the relationship between the jetting frequency and also the jetting temperature. So basically, all the combinations suggest a possible surface quality this process could produce. Obviously, this one shows a best combination. So another calculation part. So basically, the known condition for this process usually are the mass per drop, right? And the density of the metal. And also the jetting frequency, the desired width and height of the printed track. So if you look at this figure, so let's see, this is the track, and it's in a in this shape, and here is the cross section. It has a height and a width over here. So with all this information, how could you calculate the printing head velocity? So we could look into some details like this. So first of all, basically what you need to know is first the frequency, jetting frequency, and also the volume per droplet. So basically, if you assume the volume is a spherical shape, a sphere, then you can use the volume of the sphere to compute the volume of the droplet. And by multiply the two together, then you will have the volume per second, right, to jet. Then you just divide the area, cross-section area, which is in this. And after that, you will have the linear printing head velocity. Okay, if you have the printing head velocity known, so what's the drop spacing? Again, you just need to divide the jetting frequency. You just need to divide the velocity by the jetting frequency, and then you will have the drop spacing. So if you know the drop diameter and what is the drop overlap as percentage of the diameter. So to think about this, we have two extreme cases. So one extreme case is basically the two are fully overlap. That's the 100 overlap. And another extreme case is it does not overlap at all. For example, like this. It touches each other, just in touch, but no overlapping at all. So in the two cases, basically in the first one, the drop spacing is 0, right? And you substitute this drop spacing to this equation. Basically, that's the you just use the drop diameter, subtracting the drop spacing, and over this drop diameter again, and then you will have a percentage which is 100. Similarly, for this case, you have a 0%. So that's how you compute the percentage of the overlapping of the diameter. So another very interesting aspect is the thermal control for the macrostructure. As you can see, if we use this 4043 aluminum material, and if the thermal control is not good, meaning if the substrate is in a cooler temperature than the droplet, what happened is something like this. You can see there's a very clear distinction between each of the layers because there's no melting during the process. That means the first layer and the second layer will not be diffused together, which is undesired, right? You don't want to have the printed part in different segmentation instead of a whole unit part, right? Another very interesting aspect is this perception hardening for the alumina alloys. So there are 2000, 6000, and 7000 series alloys. Basically, that's the combination of the aluminum with other elements. And for these alloy, there's a phenomenon called the perception hardening, meaning after the heat treatment, the alloy could have a much more hardness or mechanical property using these alloys. But for the powder bed based method, for this 60, 61, and 70, 75 aluminum alloy, they are very different to be processed using the powder bed fusion because the heat cracking that will degrade the mechanical property of the part. But it could be processed using the VEDAR systems. As you can see here, that here shows a initial test using the VEDAR printer. Although there are some imperfection here, which are some rough kind of holes on the surface, but there's no cracking, right? Cracking means there are a kind of a very clear distinction between regions. That's cracking, but these are some smoothness problems. If we look at the microscope image, you can see it's pretty much a whole. It's pretty much a whole part. As you can see here, we print around 4 layers in this direction, right? And also here for this scale bar, it is 5 micron, right? 500 micron. That means probably those droplets will be something like this, this, and this, right? And as you can see along the printing direction, there's no cracking, and it shows a good uniformity over here. Also, there's a comparison between the part, the microstructure printed using the VEDAR machine, and also the one made by the casting, metal casting. You can see they are pretty much similar to each other. Remember we mentioned the cracking problems, right? The heat cracking problems. So that is because the elemental segregation. So basically, this describes a phenomenon that is because of the different melting point of the element. When the part is being made, there will be the segregation happens for all the elements, and that produce the crack. These are the crack showing here. So in general, if the this melting and resolidification process takes longer time, this kind of segregation will have more chance to happen. But in the VEDAR machine, because the solidification is much faster, that prevent this kind of elemental segregation, and that's why the VEDAR machine produced a part with a very good microstructure. Also, here shows some the macro hardness testing. Basically, you can see these diamond shape. I mean, this diamond shape actually is the is generated by the tools for the indentation, and using measure the angle and also the depth of this indentation, it give you an idea about the hardness. And you could look at the details at yourself. Another good property for this process is it's possible to achieve a support-free jetting. Basically, if you control the printing speed properly, when you jet one droplet, the previous one is already solidified or in the process of solidification, such that it's strong enough, the structure is strong enough to hold the newly jetted one, which removes the requirement of the printing process. And you can see this video. Take a look. See, basically this this line is in certain angle, but for many other printing process, you definitely need to print the support. But in this case, it doesn't require any support, right? Which is good property. Okay. Yep. So that is possible for the this printing process to print the lattice structure without the support material. Okay, you can see the angle become larger and larger, and it turns out it does not require any support. So as you can see here, I'm sorry. As you can see here, it shows a relationship between the drop spacing and also the pillar angles. So when the angle decreases, the drop spacing increases, and it turns out it's roughly on a same straight line, which is a very good property. And that's how this kind of printing without any support is possible. Basically, when when printing a smaller angle, what you need to do is just increase the droplet spacing, and you will have similar property during the printing process. So as I mentioned, because this support-free jetting, it is possible to print some lattice structure like this. Just imagine you embed this lattice structure in a solid shape. So all the exterior surface is still solid, but you just embed these into it. This kind of model cannot be printed using the powder bed fusion-based method, because in those methods, it is not possible to take the powder out of the solid surface. But in this case, it's definitely possible, right? In the using the VIDAR system machines.
Due to superior manufacturing and ink ejection methods, new microfine droplet technology produces significant advantages in accuracy, print quality, and speed, the most basic requirements for a printer.
Okay, so as you can see, due to the VIDAR system machine is based on the material jetting process, so it is possible to have multiple nozzle arrays on the same printing head, which will bring a lot of benefit in terms of speed and also the modeling. I mean the geometry complexity. Another future direction would be the ability to print the high temperature alloys like those steel, nickel, or titanium alloys. Okay.